Welcome to GCSE Physics, going through topic by topic. In this topic we're going to start looking at radioactivity. Now, radioactivity has been known for 100 or so years, but cast your mind back to a time perhaps before it had been invented. And a young scientist named Henri Becquerel was into all sorts of things. He was into this new photography, not like the sort of modern digital photography that we have nowadays. No, this was the stuff that used chemical plates covered in silver chemicals, and when exposed to the light they changed their properties. And he was into this sort of stuff, new stuff, and he just heard about a new discovery, a chemical called pitchblende. Had to have some, so he ordered some, and it duly arrived, but it arrived at a rotten time of the week and he was busy, so he just put it into a drawer on top of actually what was a photographic plate that he'd taken previously, and he accidentally left one of his keys in between. And when he came back and started examining the new substance, this pitchblende, he also developed the photographic plate, and to his surprise there was an image of the key there. How did it get there? Well, he thought, well, it's got to be something to do with this new chemical, this pitchblende. And so what he did, he started having a look at the pitchblende, and he got one of his scientists that worked for him, a young lady called Marie Curie, to start investigating this. And she started to discover this new substance and what it was capable of. The substance that they had was in fact uranium oxide, and I've got a very small sample here. And this isn't radioactive. Other ones that I've collected here are radioactive, so they aren't on the list because they're too dangerous. This is a wonderful piece of acrylic produced by a little company, and they've put it in there a bit of each element that is not radioactive and dangerous. And so we can see a little sample here of, there we are, uranium. And another element we'll look at later is thorium, so there's a piece of thorium there. It's a wonderful thing. So there we are, there's a little bit of uranium, and if I zoom out for you, you can see there the whole periodic table. So, quite useful. Yeah, there we are. You can see through all these little elements sticking up. Now, about this experiment. Well, Henri Becquerel decided that since he'd left this pitchblende, uranium salt, sitting on top of a photographic plate, and he had left this key on top, he got this key image made, and so wanted to try and have a look and see what was going on. Well, there was this new fandangled thing just out, sort of, they were playing with, called radio, and Marie Curie discovered that this substance in here, this pitchblende, seemed to make things on the radio. It seemed to sort of make a hissing noise, and so was coined the term something being radioactive. And that's what we're going to have a look at today. We're going to have a look at some radioactive elements and see what they can do. Once Marie Curie started having a look at these Becquerel waves, as Henri Becquerel called them, she started to discover there were more than one type of radiation. And with others, Lord Ernest Rutherford having a go as well, found out that there were basically two and then later three types of radiation, which were called alpha, beta and gamma. They discovered that things like alpha could be stopped by paper. Just a simple piece of paper like this would actually stop alpha particles. And the other one, the beta particles, went through the paper. Later on, they discovered there were in fact three types, and this type would go and be stopped by something like about 3 or so millimeters of aluminium, and this one wasn't stopped by that. In fact, you needed quite an awful lot of lead to try and stop the gamma rays, the gamma radiation as it was called. So we had various things. Now let's have a look at some of those, but to have a look at them we've got to try and detect them suitably. So I'm going to take a radioactive source, and this is my rubber I use every day, and we're going to have a look at this to see whether this is in fact a radioactive substance. Let's go and have a look at the setup that we've got. Now I have here a device to measure this, and this here is called a Geiger counter. We'll just zoom in on it, and this is called a Geiger Muller tube, and what it is simply a device that will allow us to detect alpha, beta and possibly some gamma radiation. I'm going to point it down, and I'm going to point it at this rubber, and let's bring it down fairly close so we're only going to get the rubber there. So any radiation given out by this rubber, and not much else, is going to get caught up here. I'm going to move that device out the way, more about that in a moment, and we're going to send this to the computer. So let's have a look. Now this is one I did earlier of radioactive counts, and let's just here see what we've got. We're recording the number of counts and the time, and quite often we're getting 1, maybe 2 counts, maybe 3, here 5 counts per second. Let's have a go and set this up. So we'll have here a new experiment. I don't need to save all those. We're going to use here just a simple graph. Yeah, I'll just do a graph. And what we're going to measure here is simply, I better detect my hardware. There we go, and I've got here a Geiger counter, and there's our Geiger counter. and it's not saying it's working properly. All right. Let's connect again. Right, let's see. I think the problem I have detected is that the Geiger counter is in port number. Let's put the Geiger counter in port number 2. Right, let's see if that's going to be happier. It doesn't seem to be. I love this when these things aren't very helpful. Let's get out. You can see what I'm doing. This device isn't picking up, so let's just swap it. So let's power up. I'm on port 2. There's my Geiger counter set up. The light is actually on the Geiger counter. And let's now see what we can see with this. So I'm going to put in a Geiger counter on 2. And we're not seeing anything. Right, I've got a Geiger counter. Lots of other messages insisting on popping up suddenly. Right, now I can carry on. So there's my Geiger counter set up. We don't have any problems with it, and what I'm going to do is I'm going to start to record what's going on. And we're getting 1 count, 1 count, none, 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 1 count. And I'm going to leave that going. There was 2 counts, and we're just going to leave that going for a few moments, and while it's in the background going on, then we'll have a look and see what else. So I've got a simple experiment set up. I'm just having a look at a rubber, something that we use all the time and that is not radioactive, yet it appears that it might be. So let's have a look and see what's going on. So whilst that's recording, and it'll start to compress the data so we can actually see it a bit easier, we'll have a look at these different sorts of radiation. Now, this started to give an idea that there were things inside an atom. We had something like an atom of uranium, and this had a number of 92. Let's zoom in a little bit, and this is probably uranium-238, and this uranium spontaneously was giving out something, some sort of radiation, either an alpha, a beta, or a gamma particle, ray, and this atom of uranium was changing into another element. And Marie Curie started having a look at this, and she started discovering there were not just uranium being a radioactive element, but there were some others. And she discovered one called radium, and another one which she named after a country of birth, polonium, after Poland. So we've got all of these ideas. Let's start seeing if we can discover the puzzle. Now, at that time, not much was known about an atom. We had Dalton, and he said that basically atoms were like little small solid spheres, perhaps much like a marble. So we've got all these solid spheres. Then in the late 1800s, J.J. Thomson, John Joseph Thomson here, discovered something else. And what Thomson discovered was something called an electron. And he worked out it was negatively charged. Now, what did people know about atoms at that time? Well, they were small solid spheres, and they also knew they were neutral. So this caused a bit of a problem. So what he did, he got hold of a model which he called the plum pudding model. Now it looks very much like a little cake, and if we have a look at a little cake, then this is the sort of idea that he came up with his plum pudding model. Now nowadays people don't know what plum puddings are. If he called it a fruit cake, then perhaps people would know nowadays. And he thought, well, my atom then could be a solid object, and it's got in it these currents, these electrons embedded into it somehow. I will save that one for later. So this was the plum pudding model, and it was the best idea that anyone had come up with. But we had another person on the scene, Lord Ernest Rutherford, and Lord Ernest Rutherford had some students working for him, someone called Hans Geiger, and it may not escape your notice that Geiger and the name of the Geiger counter that I'm using at the moment are probably rather related here. And another guy called Marsden, and I apologise to Mr. Marsden because I've forgotten his first name. And they set out to have a look at the new discovery and its possibilities, because Lord Ernest Rutherford had recently discovered alpha particles. He'd managed to say that they were different from the other radiation, and they wanted to try and examine what was going on. So what they took was an evacuated chamber, and in this evacuated chamber they put a small piece of gold foil. And they took Ernest Rutherford's alpha radiation source and they allowed it to go and hit this piece of gold. If the plum pudding model was correct and these were solid spheres just with these sort of electrons embedded in them, then these particles, these alpha particles, which they knew were part of an atom, so probably smaller than an atom, they shouldn't be able to go through. But they found that these particles did go through, and this was basically a covered surface. So what they could do is they could put a detector here and they could look and see what was going on. They could see these little alpha particles hitting the side and making a brief flash. All was going well, but unfortunately it didn't stay well for long, because they discovered that there were some particles that were deflected, and when they looked at those they were puzzled. And even more puzzling was that since they now knew these particles, these alpha particles, went through, very occasionally one came back, and that happened really rarely, something like about 1 in every 10,000. Lord Ernest Rutherford described this as firing the gun on a large warship at a piece of tissue paper and it bouncing back. He was that surprised, because nearly every particle went through, but not everyone did, and so they had to come up with some sort of theory about what happened. Well, I'll leave that story there for a moment, because what I want to look at is how our radiation's getting on. And you can see that we've got lots of ones, again happening sporadically. We've got the few twos and an occasional 3. And this is giving us some ideas that we're getting some radiation given off by this little rubber. So although this rubber really seems rather harmless, in fact this rubber is slightly, very slightly radioactive. Now I'm going to have a look at some other substances and see what they're like. And first of all we're going to have a look at something which is an alpha radiation source, and I've got it here. Now this is a very heavy metal rod, and it's very heavy because it's enriched with thorium, and thorium is a radioactive element. Now why am I handling this? Well, it's not very radioactive, and I don't believe in having very radioactive things around, because basically they scare me. Why do they scare me so? Well, radiation can't be smelt, it can't be seen, you can't really touch it or taste it. It's invisible, and that is so dangerous, because if you can't see, smell, taste it, is it there? And the answer is unfortunately yes, we just can't see it. And the only way of detecting it is with this Geiger counter. So let's switch this Geiger counter on, and we're going to see what happens to this. So I'm going to stop that one. Let's do a new recording, and we'll see if this makes any difference. And you might see that we're going to get a few more disintegrations per second. I put it very close to the Geiger counter. The reason I have put this very close to the Geiger counter is that this is alpha radiation. It doesn't travel very far, and so I'm giving this detector every chance to try and detect what's going on here. So let's leave that for a few minutes and we'll see how it's getting on as we go along. You can see it's just going to sort of keep producing natural disintegrations over a period of time. So let's get back to our story with Rutherford and Geiger and Marsden. They were firing alpha particles at a piece of gold foil. Let's draw this up in a little bit more detail. So if I think of my atoms, they chose gold foil because they could get the gold foil really very thin, perhaps 1, maybe 2 atoms thick. And these are my Dalton type of atoms, or in fact my other version, my plum pudding model. And what we had was some of these going straight through, these alpha particles. Now, to try and explain what was going on, the scientists came up with this idea that if an alpha particle came along and came very close to this center, it might be deflected. Most of them would just go straight through, but occasionally they're going to get so close to the center of this, well, let's give it a name, let's call it a nucleus, it gets deflected. And 1 in every 10,000 actually hit the nucleus and was bounced back and sent back the way it came. So we've got some sort of way of looking at this, and there are a few sort of models we can have a look at this and see what's happening. So Lord Ernest Rutherford came up with a new idea. He came up with this idea that the atom wasn't a solid sphere, it wasn't this sort of, wrong button, plum pudding, this little cake, but in fact what it was a small, very, very small thing in the middle, this nucleus, and going round it were perhaps some of these electrons, and we had this nucleus which they worked out was incredibly small compared with the size of the atom. And we know that our atoms are in fact incredibly small, so small that we can't see them even with the most powerful microscopes. So we can't see an atom, and this nucleus was sort of 10,000 times smaller than that. To give you an idea, if any of you have been to, let's say, any football stadium, we've got something like this. Let's have a go. Here's my football stadium, and I suppose we'll have the crowd going round it, and they're going to have the stands all around that where the people can sit. And if you put a P in the centre of your stadium, somewhere like Wembley Stadium, then an electron would be moving round probably the size of a grain of salt, probably, going round here at immense speed at a distance outside of that stadium. So that shows you there's an awful lot of space inside an atom. So we've looked at some radioactivity. We've got an idea of this atom, but what about it? Well, we're looking at this nucleus, and as the years went on, we started to discover the nucleus was actually made of, as Lord Ernest Rutherford said, they consisted of some protons, positively charged particles, and he'd already looked at his alpha particle, and he knew his alpha particle was also positively charged, and that's why they repelled when they went through. So as his alpha particle came very close to the nucleus made of these protons, it was either deflected or repelled and sent back where it came from. And so this was the nuclear model. This nuclear model didn't last very long. Other people, such as Niels Bohr, refined it, and as did others. And we discovered that certain things also happened. We found that by playing with these alpha particles, that the hydrogen nucleus had the least amount of charge. We found that basically the charge of any nucleus was shared equally between the whole number of small particles. Each gave the same amount of positive charge. In other words, the protons. As we went up through the elements, we went from hydrogen, which was 1 proton, to helium, which was 2 protons, to lithium, 3 protons, to beryllium 4, to boron 5, and so on. And they had more and more repulsion. It took a while after this discovery for James Chadwick in about 1932 to discover the other part of the nucleus, the neutron. In some respects, the glue that's holding this atom together. So we have some atoms. What is it? What makes up an atom? Well, if we look at this periodic table, and I think that light's actually a bit too bad. Can you just turn the light off for me? There we are, we can see it better. We've got our periodic table of elements, and it's arranged that they get gradually heavier and heavier and heavier as they go along. They've got more and more protons. This is the bit that causes students problems. What happens there, we get to barium, and then we go along that whole row, and then we carry on with this. And then we come along here, and then we carry along that whole row, and then go along with these. Why is it done like that? Well, I'd need a much, much bigger piece of acrylic. And maybe one day someone will make me a nice piece of acrylic with the periodic table in its full extended form. I'm one of the few people I know that puts one of those up for my students, and they seem to find it easier to put the lanthanides and actinides inside this table and work out where it goes. But this is our periodic table of elements, and you can see how many I have got missing in this set, because these are all radioactive and I don't want them. They're too dangerous. So what have we got in this system? Well, we have some protons and we have some neutrons making up my nucleus. And sometimes spontaneously out of this nucleus we get ejected an alpha particle. So let's suppose I've got a big nucleus made up of all sorts of bits and pieces here. This is all in 3D. We've got some neutrons, some protons, all holding the atoms together. And this spontaneously gets ejected. And I'm going to call that one. These are the positive ones, these are the protons, and these are the neutral ones, the neutrons, hence their name, neutrons. And this is alpha particle emission. So what's happening over on my thorium? It's going quite nicely there. We'll have a look at that in a moment. And what's happening? Well, I've got some thorium. So my element's thorium. It's got 90 protons, and we've got here 228 protons and neutrons. So it's got quite a few more neutrons than it has protons, and it's unstable, and this breaks down and gives out an alpha particle. An alpha particle has got 2 protons and 4 protons and neutrons, which is 2 neutrons. So it's got 2 protons, 2 neutrons, and it comes out. I could have written this as a helium nucleus, 4-2. And this, if we take this away, this is going to give me, if I take them away now, 2-2-4 protons and neutrons. I take away the 2 protons here, so that's going to give me 88. And element 88, if I look it up on my periodic table, we come and look at and find out that it's something else. So we hunt around and we find there it is. It is the element radium. So my thorium is giving out, here we are, thorium down here, is giving out some radium. It's producing radium. Let's just move that out of the way. So my element has changed from thorium to radium. So if I were to look at my thorium rod, we'll see that it's changing. Let's have a look and see what's going on. Well, no looks of changes there. But looking at this, we're seeing quite a lot of activity here. Let's just bring that down, and we're going to make this go up, we can see it a little bit clearer, and we're getting a lot more ones, a lot more twos, a lot more threes, and we're getting some fours going on here. I am using very low radioactive sources. I'm buying things that I can buy legally. No problem, I can buy a thorium rod to help with my welding. And if I want to, I can look at an alpha source. And we can see that. Let's have a look at perhaps an, rather than alpha source, let's have a look at a beta source. I know what I'm talking about. Let's talk about. So let's go and have a look at a beta source. So I've stopped the counter. There's my thorium rod, and I want a beta source of radiation. And this is low salt. I went and bought this at my local shop, and this is supposed to be good for you. Instead of having sodium chloride on my fish and chips, then this has got, as it tells me, 66% less sodium, and what it has instead is potassium chloride. Let's just put a little bit on here. So we've got some potassium chloride. That's harmless, isn't it? Well, potassium is a radioactive element. So if we bring this down here, in fact, I'll just squash it a little bit so I don't get my Geiger counter with lots of this stuff in there. And this is a beta radiation source. So let's set this one going just for a few moments. So I'm going to get this one going. We'll start this recording, and my Geiger counter is off, this time recording beta radiation. What's beta radiation, you ask? Well, let's have a quick look and see what we can see with this. Beta radiation, instead of being a helium nucleus, which is a very, very tiny thing, it sends out something even tinier. And what we have is, in an atom, we've got a neutron, we've got a proton, and what's going to happen is, let's just choose a particular element here, and this is hydrogen, H1, but 3 up here. It's got 2 extra neutrons, and it's not stable. This is called tritium. It's particularly nasty, it's radioactive, and what happens with this hydrogen is that it takes one of its neutrons and it turns one of its neutrons into a proton, which stays in the atom, plus a high-speed electron that is emitted. It's got negligible mass, and we've got our proton, our neutron turning into a proton, so our number, instead of going down, which where we took there, we took 2 off of the 90 to make 88, which you can just see. Here we add 1 on. So this is going to become 2, 3, which is an element of helium. Now let's have a look at the one that we're looking at, and we're looking at potassium. So we're looking at an element of potassium, and this is 4019. It's got 19 protons and the rest are made up from neutrons. It gives out a beta particle, and I can either draw it as an E minus or beta sign, and this is 0 minus 1. One of the neutrons is changed into a proton plus this high speed electron, and what I'm left with is still this mass of 40, but one of those neutrons changed to a proton. The mass of a proton and neutron virtually the same, and this became an element of calcium. On my periodic table we can see that potassium, calcium next to one another, so I'm turning potassium into calcium, and as I do so, a high speed electron is given out. Now this is really quite high speed. It's travelling at the best part of the speed of light, and although it's very small, it's going very fast, and this can cause an immense amount of damage. It can travel through round about 3 millimeters of aluminium, whereas my alpha particle was stopped by paper. You can just about get through something like 10 centimeters of air or some paper. Let's see how this beta source is getting on, and we can see it is producing again a fair amount of radiation, and we've got lots of ones, the occasional 2 and 1. Here we are, we've got 1, 3, and it's producing this spontaneously. It just happens naturally. So we have here a moment in time when it wasn't radioactive, and then suddenly we got 3 in one go. So this is quite, not very radioactive, but it's radioactive enough that I wonder, do I want to eat this low salt? Except of course we find potassium in all sorts of things, bananas, and in fact we can measure the amount of radiation in bananas, and as long as you're on 1 or 2 bananas you're fairly safe, because radiation is all around us, and sometimes we use it for some good. While that's going on, I'll show you a use of perhaps this, and this is my smoke alarm. It's got in it an alpha source, and this is continually putting alpha radiation across to my detector, and as long as the detector sees that, there's no problem. But if smoke gets in, it will stop the alpha radiation moving across, and if it does that, then the alarm goes off. You don't want me to test it, do you? So we've got alpha and beta. Now if I try looking at my alpha source, that interesting looking sort of smoke detector, in fact I will find it's got some other radiation, because hidden usually with the alpha or beta is another type of radiation, and this is gamma. Now, gamma can be either really powerful or not quite so powerful, depending on what its source is. And in some sources, it's really powerful. These are rays that travel at the speed of light, and they can quite happily go through a metre of concrete or so, which makes them trying to stop quite difficult. As you may notice, I am wearing here an alpha radiation suit for the most part. This will actually stop most of the alpha radiation getting through. In fact, as long as I am sort of a little away from this, I'm relatively safe. The beta is actually going to travel further in air. That may travel as much as perhaps a metre in air and be stopped by, well, I haven't got one, but I need this knight in shining armour. If I was wearing a suit of armour, then that would stop beta radiation. Could look rather cool going around wearing a suit of armour. Oh, what about the gamma? Well, the gamma, that means I've got to go and wear sort of a gamma radiation suit. Sort of a suit several metres thick of concrete and lead to try and stop those gamma rays. Yeah, I don't feel that perhaps a suit made of several feet of concrete and lead is really going to be that effective for walking. It might keep me safe from the radiation, but walking's going to be out. Well, so's moving. So's living, I suppose, really. All around us is radiation. It comes from the sun. It comes from the air. It comes from outer space, the famous cosmic rays. And yeah, they exist. It comes from, well, of course, nuclear weapons. Yeah, barely. They sort of don't even scratch the surface on the number. And most of it we find in the air. Depends where you live in the country. I live in a good part of the country. There's not much radiation around here. But if I were to move to, let's say, somewhere like Cornwall, which is built on granite, really good strong stuff, the granite contains within it some radioactive elements, and these break down and they give off a gas called radon gas, and the radon gas can be breathed in, and that can turn to something else and stay in somebody's lungs, and then they've got build-up of this radiation inside them, and that can cause damage, and it can cause things like cancer. More of those worries, though, next time when we start looking in more depth at alpha, beta and gamma. As for this experiment, well, it's still going on. It's still producing here quite a lot of alpha radiation, beta radiation and some gamma radiation. We've got quite a lot of sources all here going. This is just salt beta radiation, and we can see that this is a little bit higher than my rubber was. To finish, I'll show you what those are. So we'll just stop this. So this is my alpha radiation. If we do a comparison here with my beta, so I've got my beta, here is my alpha, and there is my rubber. Now what I haven't done for this is I haven't actually just measured this doing the air. And what's that like? Well, to be honest, I did, because this is what the air often looks like, and you'll see that this is not that different from my beta and my alpha sources. My alpha and beta sources are very low emitters. They do emit, but not very much. Why? Because I'm scared. I don't like the thought of keeping around in my home radiation sources. Yeah, true, I can get them quite easily, but I don't really want them. This shows us enough and we can talk about them. So, until next time, when we have a look at some more sources and some more about radiation, stay safe. Subscribe if you like watching this GCSE physics topic by topic, and I will see you next week. Stay safe. Bye bye.